Hey everyone, welcome to the member-only podcast feed for The Drive. I'm your host, Peter Attia. My guests this week are doctors Joan Mannick and Nir Barzilai. Joan is the co-founder and chief medical officer of Restore Bio, and that's a play on the word TOR, T-O-R, target of rapamycin. Before joining Restore Bio, she was the executive director in the New Indications Discovery Unit of Novartis, which we discuss early on in this podcast. She is an MD by training, receiving her MD from Harvard Medical School, completing her residency in internal medicine and infectious diseases at the Brigham and Women's Hospital. Nir Barzilai is making his second appearance on the podcast, so that name may sound familiar to a number of you. He is the director of the Institute for Aging Research at Albert Einstein College of Medicine in New York. He has spearheaded one of the most impressive longevity gene projects, which basically looked at more than 500 healthy people aged 95 to north of 110, along with following their offspring, the centenarian studies and the centenarian offspring study. Nir also has a brand new book that just came out at the time of this recording, probably a week before. It's called Age Later, Health Span, Lifespan, and the New Science of Longevity. We get into a couple of funny stories about that. Okay, this episode is one I've been looking forward to for a very long time because we discuss the two drugs I get asked about more than all other drugs combined, namely metformin and rapamycin, or the category of analogs to rapamycin known as rapalogs. Now, the reason we decided to do this as a podcast with both Nir and Joan as guests was because, of course, there were many overlaps between rapamycin and metformin, not just in terms of longevity, but also of recent note, their potential for reducing the risk of SARS-CoV-2 infection or other infections, and of course, COVID-19 morbidity. And we speculate on those things to a great deal. So basically the way this podcast goes is I want to make sure everybody has the appropriate background information on metformin and rapamycin. So coming into this episode, you don't have to know anything about those two drugs. If you do, I think you'll follow it a little bit better because these are technical. And of course, the show notes will have all of the pictures and images and things that make it a little easier to follow this. But you can come into this not knowing a lot about them, though we have had many previous podcasts that discuss these things. And then we get into kind of the clinical indications that focus specifically around this issue of how would these drugs factor into the immune response, resilience, and the amelioration of a hyperactive immune response in the presence of these diseases. So without further delay, please enjoy my conversation today with Joan and Nir. Joan, Nir, this is a first for me, and it is also very exciting. It's a first in that it's the first time I have interviewed two people virtually simultaneously. It is also incredibly exciting because I am just such a fan of your work, Joan, and obviously yours, Nir. Nir, you've been a guest on this podcast before, and Joan, I have been eagerly looking forward to having you on for probably since the moment the podcast released. So I'm grateful to both of you for making the time. And then, of course, to do this together is something that I've been a little nervous about for the past month, because I've been thinking, how do I integrate the stories of rapamycin and metformin? How do I integrate the stories of these two incredible compounds that in their most native form came to us naturally? And then, of course, we now have evolved elaborate synthetic versions of these things that have these sort of magical properties. So I have an idea for how these two can overlap. But before we do that, I think we should assume that maybe the listener is not familiar with you, Joan, and even you, Nir, though you've been on before, and maybe just help us understand a little bit about what you do. Joan, I know you're a physician by training, and you're also one of the world's experts on my favorite molecule. So help us understand how you got to be doing what you're doing.
Sure. So I was actually started my career in academic medicine. I trained in infectious disease and ran a basic science lab. But in my basic science lab, I happened to read some papers by Cynthia Kenyon that were sort of transformative for me. And I remember reading a review piece from Cynthia where she said the genetic mutations in worms that cause doubling of lifespan show that organisms have the capacity to live longer than they normally do. And I just thought that was the coolest piece of research and the coolest idea that sort of threw medicine on its head. And so I started to do a little bit of aging research in my lab, but eventually ended up at Novartis in a group called the New Indications Discovery Unit. And you heard a little bit of this from Lloyd Klickstein, but it's a unit of Novartis where they tackle areas of drug development that fall in between traditional big pharma silos. So when I got there, they said, "What would you like to work on?" And I said, "I want to work on aging." And when I first said this, I was told, "We understand that makes sense, but everyone's going to think you're wacky, so you have to pick a different area." And I was really disappointed. But a few months after I got there, the CEO at the time, who was Dan Vasella, and the head of research, who was Mark Fishman, decided they thought Novartis should work on aging.
What year was this, Joan?
This must have been 2012. Lloyd, who was my boss at the time, said, "Joan wants to work on aging." So they said, "Okay, Joan, go do something in aging." We just had this blank slate of saying, do something in a clinical trial that is targeting aging biology, and you get to pick what you want to do. So Novartis had a rapamycin analog, and there was a lot of data that mTOR inhibitors have beneficial effects on aging and lifespan. So I decided I would take our rapamycin analog, and I thought an organ system whose function I can change in a relatively short period of time is immune function. So I decided, let's do a trial and see if we give older adults an mTOR inhibitor. Can we make their immune function better? And the readout was a vaccine, the response to a flu vaccine. So that was the beginning.
Couple questions going back. I know your father was one of maybe 6 or 7 people to hold one of the most prestigious chairmanships in all of American surgery, Joan Mannick, at the Brigham and Women's Hospital. And you, of course, trained at the Brigham as well, correct?
Yes.
What was your father's response to this career change, which in effect it sort of was, right? Which was you're trained as an infectious disease doctor at a very prestigious, one of the most prestigious academic institutions in the world. And not only are you leaving academia to go into industry, but you're also making what sounds like a very rash change in your focus. Was that something you discussed with him? And if so, what were his thoughts?
I did. Everybody in my family was in academic medicine. But as you know, academic medicine has changed a lot. And I was thinking, am I going to spend the rest of my life in academia, or do I want to do something else? And I had some friends who had left and gone into biotech and told me how much fun it was. And so I was starting to get calls by recruiters, and I asked my dad, I said, should I do this? Should I leave? And he said, I was 50 at the time. And he said, "Joan, at age 50, this is the last time you have to really try something new with your career. So go for it. Academic medicine isn't what it used to be. This is like an exciting thing you can try." And so he was supportive. It was interesting.
That's fantastic.
Yeah.
The other question I want to ask you, going back to your first attempt at studying a rapamycin analog, was you chose to go after something that, as you said, could be modified in short order, which is the immune system. But of course, as you knew very well, and we'll explain to the listener, the clinical application for rapamycin was, of course, immune suppression. So what made you think that you could actually use the same drug whose clinical indication was to suppress the immune system in a transplant patient to do the opposite, which was to enhance the response to vaccine?
Novartis asked me the same question. I remember presenting this proposal to the committee that approves trials, and I go, "Why are you doing this? Why are you taking the drug that we sell to suppress the immune system and think it's going to enhance it?" It was because of all the data that mTOR inhibition has beneficial effects on aging in every organism tested. And so I said, someone's just got to do the trial in humans and see if this is true in humans. And we're going to dose this really carefully to minimize any side effects. And either it's going to work or it's going to turn out none of this translates to humans. But we got to just sort of have the guts to try it. So that's what we did.
Joan, I think it's interesting the way you frame that, which is, look, we had in 2012 at least 3 or 4 years of very good evidence that rapamycin could be beneficial to extend lifespan through the ITPs. So the interventions testing programs run through NIH. There had been several indications, either directly through administration of rapamycin or indirectly through genetic inhibition of mTOR, that you could extend the life of yeast, worms, flies, and mice. But of course, you can't do a lifespan extension study in humans. So your study that would be published in 2014, which any listener of this podcast knows and has heard me refer to as the Mannick study, the 2014 Christmas gift we all got. I still remember getting my embargoed copy the day before Christmas. That was a very important paper. And again, I still applaud you for the nerve, because it's one thing to say the following: we have reason to believe this could extend life on average. It's quite another thing to say it still enhances immune function. In other words, there's a scenario under which rapamycin did extend life across all those species and would extend life in a human on average, but still impairs the adaptive immune system so that a subset of humans are actually dying sooner due to overwhelming immune compromise, while on average people are going to get cancer later or dementia later, et cetera. In retrospect, it worked out pretty remarkably that the thing you chose to go after, which was in many ways the riskiest thing to look at, turned out to work. Was that something that you noodled at the time?
You sort of had to have the stomach to do it. And I really wanted to do no harm to these older people who were very bravely entering the trial, but you don't know till you do the trial how it's going to work out. And I tried my best to, again, dose very low or intermittent dosing that wouldn't be likely to be sufficient to immunosuppress, because figuring the only dose that will ever move forward is one that is low enough that it's safe and that it doesn't immunosuppress. And there had been data in mice, older mice given rapamycin, that vaccination response was improved. So I just said, someone's got to do this and see if this translates, because if it does, it will be the start of really being able to move medicine in new, important paths forward.
Now, Lloyd discussed the study in some detail, but just so that maybe someone who hasn't gone back and listened to that, can you explain somewhat briefly, there were 4 arms in this study. What were they dosed? What was the purpose of the dosing? How was it pulsed, et cetera? And what were you measuring? And most of all, what did you learn from that study?
So we used very unusual dosing regimens of this rapamycin analog that we either dosed at a very low dose once daily or once weekly. The reason we did this is we wanted to just partially inhibit mTOR, not completely inhibit mTOR, because when you completely inhibit mTOR, you stop T cells from proliferating and you'll get immunosuppressed. So these were chosen purposefully to limit the amount of mTOR inhibition. And what we found is if you gave it one of these mTOR inhibitors for 6 weeks, and then gave people a 2-week break and gave them a flu vaccination, they responded better to the flu vaccination. What we found is the lowest 2 doses, either 0.5 milligrams once daily of everolimus or 5 milligrams once weekly, were the best. And those gave less mTOR inhibition than the highest dose, which was 20 milligrams weekly. What it looked like is just turning mTOR down in the elderly, not turning it off, is the best for enhancing immune function.
So I'm going to hit pause on that for a moment. You mentioned the name of the drug, everolimus. It also went by another name, I believe, RAD001, correct?
Mm-hmm.
Okay. Let's bring metformin up to speed for folks so they now understand why would we want to talk about these drugs together, and why are these the 2 drugs I get asked more questions about by my patients than all other drugs combined. So, Nir, take us back to the first time you started paying attention to metformin outside of its normal clinical indication, which is, of course, an early line treatment for patients with type 2 diabetes.
Serendipitous when I came to the United States to do my first postdoc, which was at Yale with Ralph DeFronzo, what I did that year was to find the mechanism of action of metformin. It wasn't in the United States yet. Lifa Pharmaceutical just brought it in and commissioned some studies in order to show that metformin works in the US population as well, okay? Because we didn't accept anything, still don't, from other populations. And my study was the first to show that metformin specifically targets hepatic glucose production rather than, or let's say the insulin sensitivity of the liver rather than the muscle, although it's doing a little bit of both. So when I did that then, and we're talking 87, 88, I was actually doing aging there. I took people and did clamps, young and old people, but I never thought that metformin is coming back. Metformin started coming back when all those data appeared, whether it was with clinical studies or with association studies, that people on metformin in clinical studies will not develop diabetes, the DPP, it will prevent diabetes, or in people with diabetes, it will prevent cardiovascular disease, that's the UKPDS. The association studies with cancer, hundreds of studies on cancers and all kinds of cancers. The association studies on Alzheimer and also some clinical studies on MCI. And the day that I knew we have to do that was when a paper from the UK, underappreciated, that looked at almost 180 subjects in the United States into pharmaceuticals. And they looked at people who were treated by the same doctors. Some were diabetic and some were not. Some were getting sulfonylurea drugs, some metformin if they were diabetic, and controls for non-diabetic people. The people on metformin who were diabetic, were more obese, had more diseases to start with, had significantly less mortality. This kind of linked all of it together. If metformin targets aging, which we kind of knew from animals, okay, it increased health span and lifespan of animals. Many animals, 2 weeks ago, killing fish, if you give killing fish metformin, they live significantly longer. If you give it to all animals, they live longer, they live healthier. And all of a sudden, we have everything. We have all ages, all age-related disease, clinical association studies. We have mortality that just made metformin the perfect tool for us to push geroscience ahead.
I'm not as familiar with the metformin results in the ITP. I'm very familiar with all of the RAPA studies. Did metformin show benefits in the ITP?
Complicated, and I get this a lot because there were, I think, 30 studies that I summarize in a paper somewhere where we're giving metformin in many animals, increased lifespan. There are two stories. So generally, people in ITP will say, no, we haven't shown effect on metformin. But I would say there are two exceptions. One is in male mice, ITP happens in 3 centers.
Explain to folks what the ITP is. We're gonna link to it in the show notes because you're going to explain why it's so rigorous, but they're in so many cohorts. I mean, I think cohort 12 we're going to start to see the results of cohort 12 this year. I follow the ITPs a little more closely now than I used to because now they're looking at SGLT2 inhibitors and all sorts of other really exciting drugs. But yeah, explain the rigor behind it and why people put a lot of weight into it.
Well, the intervention testing program was established in order to have like preclinical multicentral studies of drugs that investigator could say without proving or without doing standard studies would say this affects longevity. So the idea is you have a committee, you get the drug, you have animals who are genetically heterogeneous because we want it to be aging and not genetic. And they're giving in the same way in 3 different centers around the United States, so that we have a standard way to say yes or no.
Those are 2 big caveats, right? I mean, lots of times things will work in one lab and then they don't go on to work in other labs. So that's an important bridge to cross. And as you said, I think the heterogeneity of the animals also adds to the rigor, because these models where we have mice that are homogeneous at each and every loci, they are so genetically flawed that you run into trouble where they become so artificial in terms of their model.
Right. In the metformin study in males, in one center they lived 10% longer. In one, also 10, one was 9, one was 11, or something like that. In one center, it was 1% less. Okay. So, it's not significant. Although, by the way, there is a power for each study. There's a power for each study to be significant because they're using 50 mice per arm.
Wow.
The second point is when they added rapamycin to metformin to rapamycin, you could say, if you think metformin has no effect.
That was cohort 7. That was a 9-month intervention, or they treated the mice at 9 months with metformin and rapa together.
The nice thing of being young like you is that you recall those numbers. They're 7, 11. That's the longest living animals, I think, so far in this ITP. They live 24% longer. Okay.
Right. And the rapa solo, which Joan is pretty impressive as well, was, I believe, 16% and 9% by gender.
Right. And I should add, it wasn't studied at the same time. Okay. So you can say there's a cohort effect. There are people in the ITP. So that's what I want to warn people against.
Is the implication that 2 of the arms showed effectively a 10% increase in the lifespan with metformin and 1 showed effectively no change? Are you saying it's possible there were methodologic errors in the 3rd site that, again, if you had done it across 50 sites, which as a purpose of a thought experiment, it might have shown a benefit, but 3 sites, if 1 goes wrong?
I want to make a bigger comment. Maybe yes. I want to make a bigger comment. It's a little bit too late to discuss mice now, right? Because we have all those data in humans. I think we have to be careful with the ITP because it's possible that, for example, in humans, metformin will have better effects than in mice. Rapamycin might have less effect in mice. So I don't think it's of the interest of anyone to start saying, some of the investors say, we're not impressed with metformin. I understand that. There are other studies that total have shown that. There's other animal studies that have shown that. There are model studies that have shown it. But who cares?
Yeah, your point is, which I think is a great point, Nir, we probably have more than enough information of the power of this intervention in humans that it's a little bit of the tail wagging the dog if we're going to get wound up about which strain of mice does better on metformin or not. And obviously, Joan, I think we're long past that point as well. And frankly, I think that's where the focus of the ITPs are moving to other more novel compounds. They're looking at nicotinamide riboside. They're looking at SGLT2 inhibitors. They're looking at acarbose, which actually looked like it did have a positive effect. So let's continue with the story, which is, and I remember the paper, of course, you're talking about because it's one that people still often reference, which is how is it possible that a cohort of patients with type 2 diabetes and all of the associated microvascular damage that would come from the hyperglycemia, the macrovascular damage that's accompanied by the hyperinsulinemia. I mean, the deck is really stacked against this patient. And yet somehow if you give them metformin and compare them to someone who has better glycemic control, presumably less hyperinsulinemia, they somehow live longer. I mean, it shouldn't be.
Right. So I want to pass forward to 2020 because we published a cell metabolism paper. The figure is open in front of me, but I want to make sense of what we try to do and go back to aging. We geroscientists kind of agree that there are hallmarks of aging, and we kind of agree on the hallmarks. We call them sometimes different. Some people say 7 and some people say 9, okay? And the hallmarks are very important, mainly because once we had the hallmarks, biotechs started forming because all of a sudden there were targets. Not only did we have the hallmarks, the hallmarks were interacting. You don't have You can target one hallmark and you affect the others. You can change autophagy and improve insulin action and mitochondria function, right? So we have these hallmarks. And in this paper, we try to do something very simple. We try to say, let's look at the mechanism of action of metformin, the papers that were published, and let's see which hallmark exactly metformin is hitting. And this was the great surprise. And I'll tell you the surprise and I tell you my interpretation. But the bottom line is there's evidence that metformin hits every one of those hallmarks. And you have a big figure there with the hallmarks on the bottom, the mechanisms of action, and all the papers that show, yeah, it does that, it does that, it does every one of them.
We're going to include that Nir in the show notes. It's a great figure. And we actually, I believe, included it from our first discussion, but it's so important that it is worth going through. Do you want to maybe talk about what you think are the three most important of the mechanisms that metformin targets? And Joan, I'm going to really ask you the same question in a moment. What do you think are the 3 or 4 most important of those pillars or hallmarks that Rapa or rapalogs are targeting? And because I think these are very important for people to understand where these drugs work and how.
I'll tell you that, but before I'm telling you that, I want to tell you that I don't believe for a second that metformin independently targets all of them. And I think that's what we should note. Metformin, let's say on the cellular level, it fixes aging, okay? Once it fixes aging, a lot of things improve, okay? Maybe the fact that insulin levels go down doesn't have to do only with metformin effect on glucose, but because autophagy has increased, mitochondrial function is better, genetic stability is good, things like that. I think when you do an experiment at the end of which you see so much effect, and there's an argument because people say, hey, it's all epigenetic. Here's the study that shows epigenetics. Well, yes, but the question is, did metformin do it? Or did what metformin did on aging do that? So for me, there are 3 major arms of metformin. One of them is the metabolic, the effect that it targets complex 1 in the mitochondria. And by that, and I'm skipping the stages, it increases AMP kinase and it targets mTOR. Okay, and everything that metabolically happens on that side.
So let me ask you a question, Nir. I've never been able to get a straight answer out of anybody on this. Do we have a dose equivalence? Because what you just said for the listener, I want to make sure is clear. Metformin is a weak mitochondrial toxin. It inhibits complex 1. That tricks the body basically into doing something, which is thinking nutrients are scarce. AMP kinase goes up. It thinks there's a deficiency of energy. We know that has a downstream effect on the inhibition of mTOR, something that we're going to talk about happening directly through the rapamycin rapalog pathway. But what I'm trying to understand is, using the cellular assays where we can read out the extent of that inhibition, do we know that 5 milligrams of rapamycin or everolimus is equivalent to 1,000 milligrams of metformin? In other words, do we have a sense of what an apples to apples mTOR inhibition looks like, even though one's direct and one is indirect?
It's a good question. I can find the answer on a cellular level because Ana Maria Cuervo, our Joan's and my friend, is using metformin as the positive control for autophagy. Okay? She actually uses metformin and not rapamycin. So she must have tried and have the dose response on a cellular level. I'm not aware, Joan, are you aware? I'm not aware. It's a good question. I don't know the answer for that.
What's also complicated because rapamycin actually isn't a good inducer of autophagy. The catalytic inhibitors are much better. So it's not just which dose of mTOR inhibitor, but what downstream readout of mTOR is equivalent. Are you looking at autophagy or are you looking at protein synthesis? Each one.
So you're saying, we're going to come back to this, Joan, when we talk about the difference between the allosteric and the catalytic inhibitors, but you're saying the way you go about inhibiting mTOR will shift the lever more towards maybe inhibition of senescence versus protein synthesis versus autophagy. So,
Right.
okay, we'll come back to that. But Nir, sorry to interrupt. Let's go back to what you were saying. So big pillar one is the metabolic complex 1 AMPK mTOR pathway.
Right, which is what we just discussed. The second is there is a decrease in oxidative stress in ROS production, and therefore also on DNA damage. That is the consequence of using a low dose of mitochondrial poison, right? So there is this aspect of that. And the third aspect, the relationship to immune function and inflammation. So those are kind of I think the major effects on metformin. And it is because by accident, it's kind of doing those two arms, the metabolic and the ROS inflammation.
You're getting a 2-for-1 there. Can you say more about the potential immune enhancement and presumably cytokine reduction if it's cytokine that's sort of deleterious?
Yes, it's doing both of them. I think Joan will give a good example. Do you want the cellular mechanism of that? Because I don't want to get into that now. I think Joan has a better explanation because we don't have we have the clinical data on metformin, but I wouldn't tell you what exactly is the most relevant target in the whole. Okay?
Okay. So Joan, let's go back to, we're still talking about either rapamycin or RAD001, a rapalog. What do you think are the places where it plays the greatest effect in longevity in terms of these cellular mechanisms or critical pillars?
Yeah, I think it's an area where we have to understand more, but one of the things that will happen with a rapalog is that you'll get less protein and lipid synthesis, and that may decrease proteotoxic stress just by having less proteins made that your protein degradation system has to deal with. Then people have assumed autophagy is another mechanism, but actually, as I was just mentioning, rapalogs don't consistently induce autophagy. It's cell dependent. So how much of a role autophagy has in the benefits of rapalog is probably tissue dependent.
Where do we think it has the most effect versus the places where we think it has the least effect on autophagy?
We look in cell lines and we don't see in many cell lines any induction of autophagy, but then there'll be a few cell lines that do have induction of autophagy. And I can't tell you, is it cells from the liver versus the cells from neurons? I don't know whether it's the tissue of origin or if it's something like the level of FKBP12 in the cell. So then the third part, it's interesting, it's similar to what Nir was saying for metformin, is there's a regulation of the SASP. So these inflammatory cytokines that are secreted by senescent cells that accumulate as we age, that is regulated in part by mTOR. So inhibiting mTOR will decrease SASP, which will decrease systemic inflammation.
When we think about that and go back to the results that you demonstrated in humans 6 years ago, how does that story make sense? So now I want to bring both the stories of rapamycin or rapalogs and metformin to, as Nir said, to 2020, where most of us are now focusing on something new. And I'll just use myself as an example. I mean, you guys have been focusing on this forever. I don't think I've thought about immune enhancement as much at a clinical level as I have in the past 4 months. So prior to COVID, most of my interest around immune enhancement, and the reason I've been so interested in rapamycin, is more in my belief around anything that you can do that's going to enhance the immune system at the adaptive level, which is what you're getting out of a vaccine, is going to help with cancer surveillance. And in as much as delaying the onset of cancer is an important pillar of longevity, that's the real reason we want to have enhanced immunity. I would say I very naively didn't pay enough attention to the mortality from even influenza. which of course is also getting more attention appropriately today. So it's not just that coronavirus is, we have a new strain of coronavirus that now adds to our burden of these. But look, there's a non-trivial chance that a 75 or 85-year-old person is going to die from an influenza virus. And now, of course, we have another virus that's going to be probably 5 times more virulent. So how do you make this link? Why is it that the T cells got better at recognizing an antigen when a patient was pulsed with a drug that is inhibiting senescent cells, or at least the soluble factors of senescent cells? Is it, as you said, maybe there's some tissue-specific or cell-specific autophagy, reduction in protein synthesis and lipid synthesis? How does that story go from the mechanistic story to the clinical story?
I think it's going to be complicated, but one of the factors on how you respond to a vaccine is actually innate immunity. And you need innate immunity to bring in the adaptive T and B cells to respond to antigen. One of the problems in the elderly is that they have a defect in type 1 interferon production after getting a flu vaccine. That's been shown by a group from Yale. And it's also been shown by another group from Stanford that all sorts of stimuli to the innate immune system that should induce interferon, there's a defect in immune cells from the elderly. What we've shown is that with mTOR inhibitors, you can enhance that interferon production and interferon-induced gene expression. And so the innate immune function, enhancing that may be one of the reasons that the adaptive immune system is working better when you get vaccinated. We've also shown that there's a decrease in exhausted T cells. We first showed that in older humans, and then Tyler Curiel showed the same thing in older mice. So there's more T cell exhaustion, and when you give an mTOR inhibitor, and particularly a rapalog, that decreases, and we don't know the mechanism for that yet.
Has anyone ever tried, this is sort of off topic, but to your first point, I was actually not aware of the interferon issue. That's super interesting. If you vaccinate older patients with a low dose of interferon, do you get around that?
Nobody's tried. You have to be careful with vaccination.
Yeah, interferon is pretty dangerous. Yeah,
right. So I think what it looks like is that there's just enhancing kind of the response to the vaccine antigen and not sort of just dumping interferon in.
Yeah, it's not the interferon per se. It's that the lack of interferon is a proxy for a failure to recognize in the first place.
Exactly.
In your 2014 paper, remind me, did you look only at T cell or also B cell assays? Did you look at neutralizing antibodies and T cell killing?
So we only looked at hemagglutination inhibition, HI titers, didn't look at neutralizing antibody, and didn't look at T cell function. We just looked at shifts in 76 different peripheral blood subsets. And it was interesting. The rapalogs didn't shift any of the subsets very much, except there was about a 25 to 30% decrease in the PD-1 positive CD4 and CD8. These are the exhausted T cells that accumulate with age.
I think I forgot that detail. So these are cells with checkpoint inhibitors on them. These are CD4, CD8 killer cells with a PD-1 checkpoint inhibitor.
Exactly. So those go down, which may be another, part of the adaptive immune system that's getting improved from the rapalog.
Yeah, which might also speak to, again, if you want to shoot for the stars, you can see some cancer protection benefits potentially with that application.
Yeah.
So Nir, explain to me the immune benefits of metformin. I've obviously, first and foremost, always thought of rapalogs as interfering with the immune system one way or the other, right? If the dose is high and frequent enough, it's going to impair the immune system. But as Joan has explained, if you learn how to thread the needle correctly, you can enhance the immune system. When did it become apparent to you that metformin, which, the metabolic benefits tend to jump out at us, but when did these immune benefits start to become really apparent?
There are papers in the 40s and 50s on biguanides that were actually looking like metformin. Remember the history of metformin, it had a cousin fenformin that seems to be more active against diabetes, but it was associated with lactic acidosis. So they went back to metformin. But in the 40s and 50s and 60s, metformin was used around the world for influenza in the elderly. And there's a lot of literature. Unfortunately, the literature is in Czech and Swedish and Philippines, and I'm not starting to get a lot of translation, but all of them were positive response to using metformin as an immune enhancer against the flu, and by the way, against malaria and some other indications. This has started really early on, and unlike what Joan did to rapamycin, this didn't really come back until recently. But we knew several things about metformin. We knew that patients with type 2 diabetes, if they get metformin, they immunize better against the flu. There is at least a study like that. And there are studies that showed, so when we talk about metformin or rapamycin, we're talking about several things. We're talking about fixing the immune decline. We're talking about the inflammatory response, right? And we're talking also with both these drugs, not about their immune function, but do they help the elderly body sustain a severe disease, right? In the case of COVID, we need all those things. We need to have better immunization, not get to the cytokine storm, and if we are sick, be tough.
Let's unpack that a little bit, because it's a great point you raise, Nir, which is if you had to wave a magic wand and make someone most resistant to SARS-CoV-2, you probably wouldn't just increase their immunity by 10 to 20%. You would reduce their comorbidities first and foremost. In other words, to use an extreme example, right? If you take a 30-year-old with no comorbidities, their probability of succumbing to this virus is infinitesimally small. It's almost unmeasurable. Whereas if you take even a 40-year-old with comorbidities, the risk starts to become non-trivial. In as much as these drugs can reduce comorbidities, they may have at least as much benefit on protecting against the mortality as they would on enhancing the immune system. And I don't think those are necessarily dependent on each other, are they?
No, they're not. Let me just say one thing. Across the world, if you're 80 years old and older, your chances to die is 180 times more than if you're 20. But let's make sure that there are young people who are dying too, okay? It's really an incredible ageism. Let me not be hypothetical. Let me give you an example. There's a paper that was published in China a little bit more than a week ago, where they looked at the 100 people with COVID that were treated with metformin, comparing them to the 178 people that were diabetic and treated and not treated with metformin.
And just to be clear, these were prospectively treated with metformin, or this was a retrospective analysis of diabetics with and without metformin?
No, and it's a good point. I don't think any one of us are saying, you get to the hospital, you get metformin. This will be a big mistake. We might kill people. They're in lactic acidosis anyhow. I mean, we don't want to do that. Those were people that were hospitalized with metformin or without metformin. So those are the 278 diabetic patients in Wuhan that were there.
And you're saying for the only difference that is apparent upon admission to the hospital is a group of them are on metformin and a group are not, but they are otherwise as close to equal as you would find them, shy of being able to randomize?
Absolutely. The only significant difference is that the glucose level in hospitalization of the metformin was higher than that of control. But otherwise, they're the same age,
okay,
gender distribution, and everything.
Okay.
And the people on metformin had 25% of the mortality. Let's change it around. They had 4 times decrease in mortality. But this is not what grabbed my attention. I went to the web and tried to figure out how many diabetic patients in China are treated with metformin. And there's an exact data. I did get a little bit indirect data because the people who give you the exact data, you have to pay them $3,500. So I wasn't ready to do that. But the use of metformin in China is between 60 and 70%. And you see the ratio of the people who were hospitalized was the opposite. So I'm thinking less people on metformin showed up in the hospital. And probably the mortality had to do more with the inflammatory, with the cytokine storm, or with their ability to handle severe disease than the immunization.
Let's think about this for a second, because obviously COVID kills in several ways. And again, when you contrast it with influenza, I think it's an important contrast, right? Influenza is probably more, and Joan, you should step in because I think you probably know more about influenza than I'll ever know. But really the issue with influenza is that it can paralyze the immune system, and it's these secondary infections that come in. So obviously there are certain strains of the flu that can kill you through the cytokine storm. But isn't the way that the majority of older patients die of influenza is just that their immune system gets sort of whacked by this thing, becomes almost somewhat paralyzed, and they become more susceptible to other infections, such as a bacterial infection? Isn't that a big part of the danger of influenza beyond just the virus itself?
Oh, we used to think that, but there was a paper that came out from the CDC in New England Journal in 2015 that looked at what actually causes pneumonia in the elderly that gets them hospitalized. And it's not a combination of virus and bacteria. That is some of it, but the majority is a virus. And the most common virus is actually rhinovirus, which is the cause of the common cold. And it's that the elderly just can't handle viruses the same way as younger people do. So they can actually die from the flu.
Just to make sure I understand what you're saying, they don't have to get bacterial superinfection.
No, even with rhinovirus. And the virus itself causes damage, and then the immune response to the virus also causes damage. So not even without cytokine storm, you can kind of get immune-mediated damage.
And I want to come back to Nir's point in a second, but I just want to go down this path a little further. As you look at the damage from specifically SARS-CoV-2, seems like a much worse virus in the sense that it causes much more direct damage to the pneumocyte. So you now get much more direct damage to the end organ. And that's not saying anything about all of the other disadvantages of it through its transmissibility. Do we believe that at the immunologic response level, it is eliciting a much more toxic autoimmune response or cytokine response than, say, influenza, which itself is quite nasty?
The coronavirus infects cells, including lung cells, and that causes direct damage from the virus. But then the host response to the virus is good because it will get rid of the virus. But if it gets excessive, you'll get cytokine storm, which will cause major life-threatening consequences independent of the virus. But if you can enhance the ability of the host to sort of get control of the virus very quickly, the thought will be you won't be susceptible to that cytokine storm, and you'll, stay with mild disease.
So based on the little bit that we know about the ability of a rapalog to enhance immunity through these early stage clinical trials, and then Nir, based on what you know, based on these uncontrolled trials that have more relevant recent data because they're dealing with the virus of interest, what are your best guesses about the particular places where each of these agents is exerting their benefits? So starting with you, Joan, where do you think a rapalog has the greatest potential to reduce the risk of succumbing to COVID?
What we also see is that in people who get mTOR inhibitors, their innate antiviral gene expression is enhanced when they get a viral infection. So what this suggests is early on, like as post-exposure prophylaxis or in a prevention mode, the rapalogs or the mTOR inhibitors may have benefit by boosting the body's response that is defective as we get older to the virus, so we can clear it better so that we don't go on to get severe symptoms from the virus.
Okay. Does that suggest that, well, I want to come back to this because I want to talk about it in the context of RTB 101 and how you would think about where I'm going to come back to, Joan, just is going to be around how do you think about dosing this? Is this something where we think about these as maintenance drugs that people probably ought to be on in anticipation of such a thing versus a drug that comes in from a treatment standpoint? So while we park that thought near, let's go down this sort of same path on metformin. So one thing that you suggested from the cohort that you just described in China is, first of all, the people taking metformin were disproportionately less severely ill. So fewer people who take metformin wind up in the hospital, and the ones that do end up doing better. That's
Let me add to it that I've been looking for this literature, and I've started my own study at Einstein because I got emails from Spain and Italy from physicians who noticed the same on metformin. And
so this is like January and February when they're hitting that first wave.
Right. They said, do I hear about it? And I begged them, you should publish. I should say another thing, and that kind of links to the mechanism. There's a study that was published yesterday in MedRxiv. So it's a study that was submitted, right, and not reviewed, okay? And in fact, when I'm reading this study, you can ask me questions there and I wouldn't know because they don't give enough details. But they show two things, that women on metformin have about more than 20%, 21, 22% less mortality. This is from Minnesota.
I'm sorry, this is mortality due to COVID-19 or all?
COVID-19. They had access to 6,000 patients through the University of Minnesota. I'm sure they're all not all in Minnesota. Access to 6,000 patients, and they found that females on metformin have 21% less mortality. Now, I don't know if those are only diabetic patients or it's only women on metformin. I don't know what's the one here, okay? But there was a sex-specific decrease in mortality. But even more important, they had 80% decrease in plasma TNF-alpha levels. That was also highly significant. That kind of ties, I don't know why they measure only TNF-alpha or if they measured only TNF-alpha, but there's a kind of a link to the inflammatory response.
Again, let's think about that. Is there any indication, by the way, that metformin alters ACE2 expression?
No, there's no indication of that. I actually put ACE2 and metformin to see. There is one of the first studies that came on drug in COVID was an in silico analysis that put 76 drugs or something like that, including rapamycin as metformin, as potential interacting with the COVID SARS-2 pathway.
Basically, the fact that there isn't some apparent link between metformin and its ability to alter the tissue target, it would seem that any benefits that you're describing that turn out to be real are either based on immune enhancement or immune modulation. Either you're turning up the immune system when you want it to be turned up or toning it down when you need it to be toned down, correct?
Yeah, as long as you don't say it's the same it's the same mechanism that you turn on and up. I think
No, that's my point. These are different. And what I'm really trying to tease out is, first of all, is that the right way to think about it? That's how I would think about it. Secondly, if so, which of those two do you think it's acting on?
Well, I think both. That's why I made the point that at least this study and some of the things I hear from Europe suggest that less people in metformin are hospitalized. So they get their immunity is better, right? Mm-hmm. And then when they're in their hospital, less of them go into an inflammatory response. And the time course is different. Remember, it's when you get the disease and the inflammatory thing is like 5 days later, right?
Did the Chinese data that you referred to that were published about a week and a half ago, obviously your analysis suggests the first part of that. Your analysis, which is looking at the proportion of patients in China taking metformin versus those hospitalized, would suggest the immune-enhanced piece of that. Do you have data beyond the obvious, which are the survival data, that suggest that you actually saw attenuation of a pathologic immune response? For example, did they measure cytokines in the Chinese cohort?
No.
It was just the outcomes.
No, it was just the outcomes. Again, I want to say, I'm interpreting lack of data to suggest that maybe not enough for the hospital, but I don't know that. Maybe in Wuhan only 30% take metformin, right? And the others do not. So let's not make too much out of it. I use this more to say that we really need to look at both issues, the immune response and the cytokines. And then the third is the ability of the body to sustain severe disease.
And you were going to say something, Joan, on that.
Oh, I was even wondering, in someone who's critically ill, would they not receive metformin anyway? Would it just be discontinued and ICU patient?
I want to say about that, we've done this study, we talked about it before, Miles, where we gave metformin for 6 weeks and then crossed over to elderly people, we were taking biopsies and we're doing transcripts, 2 weeks off and then 6 weeks. And there was an effect of metformin in those who got metformin first. On the placebo results, there was still lingering effect of metformin. Mm-hmm. So I think, okay, you stop metformin and you should, and we shouldn't say the people should get metformin to prevent COVID, not to treat COVID. But I think that when you so substantially change the aging phenotype of a cell, it's not that you stop and it goes back to old. So I think it's okay. 5 days later, it can still be effective.
Yep.
So, Joan, what is your take now on basically the role that a rapalog could play in the prevention of mortality from COVID-19 along these two axes? Let's posit that a rapalog plays no direct role in inhibiting the virus from getting into a cell. It's not going to play a role on that pathway. So instead, we focus on these two immune properties, the ability to enhance immunity to fight the virus versus the ability to tone down the immune response when it becomes overexuberant. How do you see those two playing out?
First, there is some data that mTOR inhibitors may interact directly with COVID and inhibit replication. But
meaning the virus, the SARS virus.
The virus. There may be a direct antiviral effect that's seen with CMV and BK virus in transplant patients where they have lower CMV and BK viral infections, probably because of a direct effect of mTOR inhibition, because the virus needs
That's interesting. Is there any evidence of that in the other 4 coronaviruses that commonly occur?
No, but to Nir's point, there have been a bunch of transcriptomic, metabolomic, proteomic, big data analyses that have identified mTOR and rapalogs as potential drugs that would interfere with the replication of SARS-CoV-2.
Okay.
And Joan, in your study, you also had less coronavirus as an outcome.
Right. So that's what we think is probably not a direct effect on the virus. That's immune function.
Okay.
I was getting before, in studies where we've looked at laboratory confirmed respiratory tract infections, in our phase 2 study, we looked at 17 different viruses that caused respiratory tract infections in older people. And 4 of them were the common coronaviruses. And what we saw was that mTOR inhibitors upregulated antiviral gene expression and reduced the incidence and severity of coronavirus infections. SARS-CoV-2 wasn't circulating at that time.
Right. And if I recall, Joan, and this would be just as good a time as any to go back and talk about RTB 101, which was the drug you're talking about. But it was the coronaviruses had a huge difference between drug and placebo, as did the rhinovirus you've already alluded to,
right,
along with RSV. And I think one of the influenza strains, right? Not both.
Right.
So let's do that. Let's detour back for a moment and talk about what came out of the RAD-001 trial, which is the one we talked about in 2014, that showed enhancement to flu vaccination. And then what this new compound RTB101 is. You've already made one reference to it when you casually mentioned that it's a ATP competitive mTOR inhibitor as opposed to an allosteric inhibitor. You might have to explain to people what that difference is, but we've now talked about it twice. So I think it is worth an explanation, and I think it does become germane. And then let's talk about the difference between the 2A and the 2B study.
Sure. in that first study where we just looked at rapalogs to enhance flu vaccine response, we noticed in a clinical trial, you always collect adverse events reported by people. And we noticed that the people who were getting the mTOR, the rapalog, were reporting fewer respiratory tract infection as adverse events, and they weren't flu. They were just all-comer respiratory tract infections. So it made us think, hey, if this is enhancing immune function, it's not going to be enhancing just the response to a flu vaccine. It's probably going to enhance the response to all sorts of different pathogens. So in our phase 2, we said, let's not only look at vaccine response, but let's actually look at infections that occur to see, are we decreasing infection rates? And in that phase 2, we also said, if mTOR inhibitors really do enhance immune function, this shouldn't be specific to a rapalog, which is a drug that changes the conformation of mTOR, and that's how it inhibits it. And we said other kinds of mTOR inhibitors, which block the catalytic site, mTOR is an enzyme, and they block the catalytic site, they should also have benefits if this is really an mTOR-mediated effect. So we looked at a rapalog, and we looked at a catalytic inhibitor called RTB101, and we looked at the two together. And we looked not only at vaccine response, but we looked at infection rates for a whole year.
Now, RTB101 also has some PI3 kinase inhibitory properties as well, doesn't it?
So in a biochemical assay with an isolated enzyme, it inhibits PI3 kinase. And Novartis made this drug in the hopes that it would be a dual mTOR PI3 kinase inhibitor for cancer patients. But when you bring it in cells and in humans, you need much higher concentrations of RTB to inhibit PI3 kinase. And at the concentrations that are achievable in the clinic, it's mostly just a TORC1 inhibitor. It doesn't even get concentrations easily high enough to inhibit TORC2. So there's two mTOR complexes that contain mTOR, and this is most potent inhibitor of the TORC1 complex.
Now, you achieved that in the first study by using the rapalog dosed intermittently at the lower doses. So I know the higher dose, which was 20 milligrams, you probably still get some C2 inhibition, but at the 0.5 daily, you probably don't get much. At the 5 weekly, you're probably mostly just hitting 1, correct? And not hitting 2.
Exactly. Like we didn't see any real hyperglycemia or hyperlipidemia, which are the TORC2 side effects.
So is it safe to say that at the doses you give RTB101, it has comparable mTORC1 inhibition to RAD001 at 5 milligrams weekly? Would that be the closest comparison?
Probably more 0.5 milligram daily, because we give RTB every day.
Got it. Okay. And the reason you give it daily is, of course, the selectivity, the catalytic selectivity.
And also, it has a shorter half-life. Its half-life is 4 to 6 hours. So if you dose it once a day, it's inhibiting TORC1 for a shorter period of time than everolimus. And if you give it twice a day, it's a little bit more persistent inhibition. Now
explain, were there two studies, one that was combining these two, RAD001 plus RTB101, and then there was the Protector study just RTB101 by itself?
Correct. So we had 2 phase 2 studies looking at RTB alone and in combination with everolimus. In the first study, the combination looked the best when you dose it for just 6 weeks. In the second study, when we extended dosing for 16 weeks in a sicker population, the RTB alone was better. So in both studies, RTB alone decreased respiratory tract infections. And in one, the combination did, and the other, it didn't.
So the study that did not meet its hard outcome was RTB101 alone, but not for vaccine response. It was for total respiratory tract infections?
No, and that's part of the problem. For our phase 3 study, the FDA said we don't want an endpoint of laboratory confirmed respiratory tract infections where we had seen the benefit. And they said people don't care, this was pre-COVID-19, if a respiratory tract infection is laboratory confirmed. All they care about is how they feel and function, and that's their symptoms. So what you have to do in the phase 3 is show you can decrease respiratory symptoms that are consistent with a respiratory tract infection, but don't have to be due to a respiratory tract infection. And we couldn't decrease the total respiratory symptoms that the elderly have. What it does look like we did was decrease the severity of the symptoms.
But you weren't powered to detect that, or were you?
If you're looking at the laboratory confirmed infections, we were underpowered because there weren't very many. I think what the mTOR inhibitors are doing is not stopping people from getting infected, but if you get infected, there's a better immune response and your symptoms will be milder.
Yeah, I mean, Nir, I've heard you say that, because I want to come back and really talk about TAME in some detail, but it's a bit of a blessing in disguise that you didn't start TAME a year ago, because obviously it would have been interrupted as a result of this. I mean, all the clinical trials that I've been following closely have been interrupted by this. I follow very closely, for example, the clinical trials looking at liquid biopsies in cancer, and all of a sudden these trials are completely interrupted. So there's that component to it. Of course, the flip side of that is, depending on how large the study is, you might have actually inadvertently got another look at an indication you weren't necessarily thinking about. And I guess my question for you, Joan, is, do you have enough subjects from the protector where there might be some lingering benefits, or do you think that window has closed and there's no benefit to going back and looking at the patients who received active drug in protector to see if they had any downstream benefits in terms of protection from SARS-CoV-2?
We haven't even thought about it. You're the first person to suggest it. No, it's a great thought.
When did those patients finish enrolling?
In November, last November.
Like November of 19?
November of 19.
And those were in New Zealand too?
New Zealand and Australia.
So New Zealand doesn't have the COVID yet, right? Maybe.
No, it had it, but it
was pretty mild. They were very well controlled.
But we also had I don't know how things are going in Australia. So we also had sites in Australia.
I mean, I guess it would be an interesting exploration because, again, this is one of those things where you now wonder if you repeat the protector study, either as it was done with RTB 101 or with RAD 001 or in combination, but you now do it specifically for this virus, do you get a different outcome?
And I do think, we're learning as we get more and more data. I think we're actually doing a trial in nursing homes now, looking at severity and not just incidence, because I think what's happening is once you get infected, you're better able to upregulate that interferon-induced innate immune response. And my guess is that's why you're having less severe symptoms. It's not happening before you get infected.
I want to make, I think, an important comment, because we spend time, and Peter, you try to really look at those drugs apropos mechanisms of COVID-19. But I think that what we are trying to sell out there is that we are reinforcing, we're not fighting the virus, we're reinforcing the host. Okay, we're defending the host. And the claim is that what we saw to influenza is relevant to COVID, because after all, what's the difference between the people who are dying? It's their age, right? It's the biology of aging that is different. And by the way, you previously said multimorbidity. For me, multimorbidity is how old you are biologically. That's all it is. Okay, 65% of the people have more than two diseases, and 65% have more. Chronological and biological age are different. So I really think that part of what we have to discuss is the fact that we are defending the older individual. Whether there's something specific that can help is really great, but this goes not only to the immunity, doesn't go to the inflammation, but goes also to how do we develop vaccines now? Because the vaccines that I'm seeing developing are not considering the older host in several ways. The New York Times today says that they even are going to test it over the age of 65, okay? I think the vaccine is going to be such a trap, and the way to go over that is either realizing how to do it with the biology of aging, and there's a way I'm ready to discuss with you some mechanisms, or the elderly have to be on metformin or rapalog in order to get their immunity going. I think this is the next disaster. If we have a vaccine that doesn't protect the elderly, we did nothing.
Let's talk a little bit about it. This is a topic that's near and dear to my heart. I'm getting involved in a study that's looking at a question from a slightly different angle, which is what's the durability of immune response? historically, as you guys probably know, coronaviruses are not exactly the most robust at inducing durable immunity. In fact, if you remain immune for a year, that's considered reasonable. This poses a huge problem, which is, what if after all the trouble of getting SARS-CoV-2, getting sick with COVID-19, bouncing back, you only have a year of immunity? The probability then that a vaccine is going to provide lifelong immunity, the way we get it from several of our most famous vaccines, seems quite low. And so now you're in a situation of saying, well, gosh, what is the efficacy of a vaccine going to look like? Is this going to look like a 30% efficacious vaccine that you're going to need every year? Is it going to need to be supplemented by monoclonal antibodies in the most high-risk populations? I think we're all basically saying the same thing, which is there's a real risk here. So taken in order, what is the probability this virus is going away? 0. I mean, it's somewhere between 0 and epsilon. But the likelihood that SARS-CoV-2 magically, mutates its way out of impacting humans is so low, it would be foolish to entertain that. So we now have a 5th coronavirus that's here to stay, except unlike its other 4 cousins, this one can really whack you. And then let's assume we can make some safe and efficacious vaccines. Are they really likely to keep you protected for 5 years, 10 years or more, even without the genetic drift? Based on what we know of other coronaviruses, that seems unlikely. Again, we're going to do a study to try to answer that question. But I think we do have to get ready for something that says, oh man, we could be in a really unpleasant place where we never really naturally acquire herd immunity. And if that's true, not to fearmonger, it means we need a better strategy around immune enhancement. I mean, that's sort of my general take on this. Would you guys tone that down or ramp it up?
I think it's quite a reasonable stance. And I think, finding things that help generate persistent immunity is going to be important.
Especially for the vulnerable population. I mean, that's the part that I think is really frustrating, is you were all struggling to come to grips with, well, what is the implication of this for school kids, where the restrictions seem so impossible to manage that it seems ridiculous, right? Like a 7th grader shouldn't have to be, completely quarantined in the manner that we would think about quarantining a 70-year-old. So we have to be able to now think about immune-targeted therapies for the most immune vulnerable. I mean, I guess, Joan, how do you now think about juggling these things? Because I know that prior to COVID, you guys were already looking at an indication in Parkinson's disease, right? Mm-hmm. Help me understand from a preclinical standpoint what that was about, but then also, how do you now think about juggling resources, including time and just cognitive bandwidth, around Parkinson's, which was sort of the path you were on, with now something that seems even more pressing and maybe even closer? I don't know if you think this is closer just based on the data.
Yeah, we have, just reams of data now of using mTOR inhibitors to enhance immune function in older people, safety data and data on incidence, severity of respiratory tract infections, and a lot of biomarker data to start understanding what is actually going on in the immune system. So we're farthest ahead there. When we used to go and try to raise money for, doing this kind of research, investors would just, we'd mention respiratory tract infections and they would start to yawn. Like, nobody cared. They cared about cancer and they cared about rare diseases, but they thought respiratory tract infections were boring. The nice thing about COVID-19 is it's making it obvious why enhancing immune function is a really important area, and giving us a little bit more bandwidth to see if we can get it right. For the Parkinson's disease, it turns out neurodegenerative diseases, there's an accumulation of toxic protein aggregates. And if you enhance autophagy in preclinical models, that has benefit. I mentioned rapalogs aren't great at inducing autophagy. RTB at high doses is very good, but it's hard to achieve those concentrations in the brain. If you use the two of those together, you can lower the concentration of RTB that's needed to induce autophagy, so you don't have to get so much across the blood-brain barrier. And that was the reason we did the trial of that combination in Parkinson's disease.
Now, Matt Kaberlin wrote a really elegant piece, gosh, it's probably been a year ago now, where he said, and I thought it was just great, but I'm obviously biased, that like, why in the world are we not pouring more resources into rapalogs and Alzheimer's disease? And he basically gave the argument you're giving, which is when you look at their potential to both ameliorate and potentially clean up a lot of the protein aggregation, disaggregation that's occurring in the CNS, it seems like almost a crime. When you look at some of the cockamamie ideas, especially that are being proposed to treat Alzheimer's disease, Nir, that brings me to a question for you about this. What is the state of the art of understanding the role of metformin in the risk reduction for Alzheimer's disease beyond the obvious? In other words, anything that normalizes glucose and insulin is going to have a direct benefit on dementia. And you mentioned MCI earlier, but do we have any other data that suggests that metformin should be a part of the toolkit to reduce the risk of Alzheimer's disease?
Not directly. There are several other funded NIH projects that will take a couple of years to look at people with MCI. The two studies that looked at MCI, metformin for 6 months and one for 9 months, had decreased deterioration in some of the domains of Alzheimer's. For both of them, name recalls, which is a real problem for me.
Are you saying you're an MCI, Nir?
No, I'm on metformin. But I think it's a common problem to some of us. The Alzheimer is more complicated. There are several, the good studies all showed that people on metformin have less Alzheimer's. There are some studies that don't show that, and there are two reasons for that, or possible explanation. One, they're from China, okay? Either it's not similar mechanisms, genetics and environmental interaction somehow, possibly. But more likely is that, think about it this way, you really have to do it good, because if metformin delays mortality by 20%, okay, that means you'll get more people on metformin lingering longer, right? And it might be just that effect that all of a sudden the people with Alzheimer are hanging around longer. So those studies, it's kind of why we need clinical studies and not associate studies.
Absolutely.
Because they're so dependency of things that we're looking at.
That's a great point. What have you two ever discussed about the combination in humans of metformin and rapalogs? What are your thoughts on that? Are these drugs that are accretive? Are these drugs that should never be combined? I mean, I'll just share personally my experience. I've taken both together. So Nir knows all this stuff, Joan. I started taking metformin in 2010. That's when I sort of became pretty convinced about the data. I started taking rapamycin in, I want to say 2018. It's been about 2 years. That was a bigger thing for me to jump, but I stopped taking metformin around the same time, though not because I thought one shouldn't be on one or the other. And Nir, I want to come back and talk about why I stopped taking metformin. So see if you can talk me into taking it again. But I want to give you all my reasons why I stopped. But what are your thoughts on how these drugs would combine in humans?
Well, for me, it's simple. Look, as you already know, we're trying to advance the field, okay? And the reason I chose metformin, it's not because it was the best drug. I think rapamycin should be better drug. But it's because we didn't want to kill anyone on the road to success. That's really is. And I think combining metformin and rapamycin is like the rapamycin part is the one that we want to be careful with. But on theory, look, that's where it's going. Let's say TAME ends, okay? And let's say the FDA agrees that aging can be prevented, age-related disease can be prevented, and everybody can take metformin because it's so cheap. I think the next stage is combination of drugs, better drugs, timeline, different timeline. When is the best time to start rapamycin? When is the best time to start metformin? Senolytics, we don't want to start when you're 20 years old. There's not an obsolescence there, right? So there'll be a lot of calculation. So I'm not against that. I'm focused on achieving a goal that the FDA Metformin is a tool to pave the road for an indication. That's all I'm trying to do. In the meantime, I'm a believer in metformin. But
tell me where we are with TAME. Joan, will you remember that I want to come back and hear your opinion about the combination? Because I do, and really, I'm asking from a mechanistic question. Nir, I appreciate your point, which I think is the voice of reason and wisdom, which says by doing them sequentially in parallel like this, we can risk stratify a bit better. But I'm also just interested in just sort of speculating mechanistically. But Nir, give us kind of a brief update on TAME and help me understand, by the way, metformin, as you said, is a free drug effectively. Who has a financial interest in this? I mean, there's no drug company that could be interested in this, right? It has to be sort of philanthropic or NIH driven, correct?
First of all, I will quote you on what you said. I feel totally lucky now that somehow metformin was delayed. It was very frustrating, but it's almost, we get help of God. The second help, I hope, is this COVID-19 story. So we're lucky in a way. The company that's going to give us the metformin, which is cheap, and the placebo, which is expensive, is Merck Germany. Okay, Merck Germany holds the world license for metformin. So they're contributing it, which is not a simple contribution. Part of the problem with TAME is that there's no commercial interest. So nobody was going to pay for a phase 3-like study, right, for 5 years. And the NIH, which is a longer story, and I don't think I told all of it last time, but the NIH, bottom line, found that it's too risky to do this study. The major comment, what if it doesn't work? Well, if we knew it will work, we didn't have to do the study. Interestingly, we know it works separately for each one of the age-related disease and mortality. So I don't know what chance we were looking. And there's also politics of the NIA, I have to tell you. There's also politics there. So this is what we're doing. American Federation of Aging Research has nonprofit people from nonprofit and non-industry that are supporting TAME. In fact, we're expected to get the money any day now.
Sorry, what is the total budget for TAME going to be?
So we have a study, $78 million, that was our initially budget. And now we have 3 pockets because we had 3 specific aims. The primary outcome is the FDA outcome. It's prevention of age-related disease and mortality. Okay, this is about $35 million, and this is the AFAR grant. The second part is biomarkers. We want to make sure that we know what are the biomarkers for metformin action and for aging. And this was funded by the NIA, and we'll get the money once the TAME is funded in order to take plasma and blood and DNA and everything and be able to do omics and other things and find biomarkers. The third part could come later, and this is the geriatric part. How many hospitalization and what's the ADL and the frailty index and things like that. We have enough power to do it at the end of looking at people at the end and people with metformin and without metformin. But of course, it will be better to start at baseline. But we're not funded for that yet.
And how many subjects in each arm?
Well, we are discussing now. We are planning 3,000. Our power is based on 3,000 subjects. But we might have enough money to increase to 3,500 subjects with the hope that it might accelerate our result. It's not necessarily so. It's possible that you need the time that you need, but it's 3,000 subjects now, but could be more later.
And does your budget permit for serology testing or other things to now include potential, given that your subjects, I assume, are older? You have a beautiful population to also study the effects of metformin on immune function, specifically with respect to COVID-19.
Right. So the way we organize the study, and this is also in negotiation with the NIH, we will have ancillary studies that will be reviewed. Sometimes you need only 250 people, so it can be in one center. We have 14 centers. And part of the examples we gave is actually immunity. That was the example we had. It was against the flu. But of course, now we're talking about if we start before immunization, we'll immunize for influenza the first year and see the response, and then for COVID-19 the next year and see the response.
Joan, back to you on this other question then. What do you think about the idea of could there potentially be a benefit in combining metformin with a rapalog, knowing what we know now about the potential pillars? There's not a huge amount of overlap, at least in the most fundamentally important pillars, right? I mean, the two really clear things that rapalogs are doing is impairing synthesis and probably inhibiting SASP. I mean, those two seem undeniable. And then there's probably some autophagy depending on the way that you inhibit and or the tissue. So how does that fit with the double down effect of the metabolic side of metformin along with the potential increase of ROS and some of these other benefits around inflammation that come from metformin? Is there a synergy with these things?
Yeah, I don't think we know enough. As I recall from the ITP study where they used both, the effect was driven by one center, but I had seen that data early before the whole study was finished. I have done analyses of people who are getting the rapalogs or RTB who are on or off metformin just to see if I could see a difference, but we're way underpowered, so I can't say anything yet. And Nir, you may understand the biochemical rationale for using the two together, but I do think, to Nir's point, every drug that has a biologic effect has a side effect. And so if you use two drugs that have a biologic effect, you're just going to get more side effects. So you got to make sure that the benefits outweighing the risks.
Let me give you an example. If both of them are enhancing autophagy, okay, which is good and it's synergistic, but the patient has cancer, then it's when we want to stop autophagy.
But Peter, can I ask you a question?
Yeah.
I love hearing people who are taking rapalogs or metformin. What did you notice on each of them?
Yeah, why did you stop?
Sure. So, well, I as I said, I started metformin in 2010, the spring of 2010, May of 2010. I remember it very well, actually. And I stupidly just started at 2,000 milligrams a day. I didn't escalate the dose. So I remember having lots of nausea for about 2 months. And again, some people, if they just go straight to a high dose, they do feel nauseous. Others, usually when I put patients on it now, we titrate them. We go 500 at night, then 500 BID, 1,000 at night, 500 in the morning, et cetera. So that was my first. Beyond that, I didn't even notice I was taking it. So never a side effect again. So why did I stop it in 2018? In 2018, I started to very, very closely track my lactate levels during exercise. And in particular, I was tracking my lactate levels during a type of exercise called zone 2 exercise, which is when you're basically trying to see how much work you can do under purely aerobic conditions. The definition of this is actually how much work you can do while keeping lactate below 2 millimole. I used to do a lot of lactate testing on myself when I was an athlete, so I was familiar with what these levels looked like, and I was kind of surprised at how high my lactate levels were, even at baseline. You know, I was walking around at a lactate level of 1.6 millimole. Now, it would dip a little bit when I would start exercising, but I was realizing that I just had, higher lactate levels than I wanted to. And I thought about it and I was like, wait, this is obvious. I'm taking a mitochondrial toxin. Of course, my lactate levels are going to be higher. So then I did the experiment, and I did all this sort of talking with a friend of mine, Inigo San Milan, who's also been on the podcast, of stopping metformin and starting it again just to see if we could reproduce the effect. And sure enough, it was clearly the metformin that was allowing my lactate levels. And you do this at a fixed power level, right? So on an ergometer, you would just say, look, at this many watts or this many miles per hour on a treadmill, you could watch your lactate level go up and down as a function of metformin. And then, we looked at a couple of studies and you saw that, look, there were some things that metformin was blunting with respect to exercise. some things I didn't care much about, but you could certainly see, I think in the master's trial you saw, and Nir, I'd love for you to talk about this trial a bit, some blunting of hypertrophy, so muscle mass, though I don't think they looked at muscle function, so maybe it wasn't having any impact on muscle function.
They hid it well.
Did they look?
Yeah. So we have a paper in review now that, by the way, took us a lot of time because the authors disagreed on the interpretation of the same data. Joan, it was everybody exercised, half of them with metformin and half without. And they got a grant because they said it's going to be synergistic. Through AMP kinase, we're going to have better effect. The people with metformin and exercise are going to do better. And what happened? The people that were exercising with metformin had significantly they all increased muscle mass, but they had less muscle mass. In the supplement, they show you that the function was actually the same. In other words, gram of muscle when you're on metformin is doing better work than gram of muscle when you exercise only. It was a little bit hidden. And that's why I took this study and I said, I want to see the transcript. And the transcript all showed what you kind of missed in this whole idea. Metformin is decreasing mTOR and exercise is increasing mTOR. So all the mTOR transcripts were higher in the exercise-only group and were blunted by metformin.
And were these elderly or young?
75 years old.
75?
Yeah, all elderly.
Because there's other papers where mTOR inhibitors don't decrease muscle mass in older people. So that's, it doesn't seem to...
Just a minute, let me just tell you the main result. 516 of the transcript were different between them. They were only in the metformin group. And those were the transcripts that we want to see with aging, such as transcripts for autophagy. So basically what I'm saying, in this elderly population, what the metformin did is kept the young profile of the muscle. And at the end, maybe you had less muscle, but the same function. But you gained by metformin protecting 500 transcripts that are aging transcripts.
And then what do you make of the changes in aerobic efficiency? Wasn't there another study, and I was thinking while you were talking I could find it, and I just can't find it. I think it's the Konopka, right?
From Colorado, a group in Colorado. I forgot their name. But what you said about lactic acid, I saw it in my first study with the Fronzo. All our patients increased their lactic acid. Some of them above 2, some of them below 2. All of them increased. And the increase in lactic acid was associated with better glucose control.
Interesting, yeah.
It's one thing to have lactic acidosis.
And to be clear, my concern was not at all lactic acidosis. It was, are my mitochondria less efficient as someone who is exercising so much? So it was really my concern was this. I still have many patients who are taking metformin. My thinking became, if you are metabolically healthy and if you are exercising to a maximum degree, if you are maximizing the dose of exercise, is there additional benefit that comes from metformin? Or is this a drug that is better reserved for people who are not taking the maximum dose of the drug known as exercise? That basically is my question.
My answer is there is an independent effect of metformin when you're exercising, at least if you're those people. And that's why I'm taking metformin and I'm exercising daily.
And when you say those people, Nir, you mean people above a certain age?
Yeah, those were a group that were above 70 years old. Okay, the study that I'm telling you. I don't know at 40, 50 and stuff, and I don't know about maximal exercising, right? I didn't describe a study that you were the example of the patient.
And what dose is TAME going to be testing 1 gram twice a day?
1,500 milligram of extended release. They'll get 3 tablets every morning or every night, whatever they choose. 300, 500 milligram extended release pills.
And is that what you take personally, is 1,500 milligrams?
Yes.
Okay. So then going back to your question, Joan, when I started Rapamycin, and I think I've talked about this maybe even with Lloyd on that podcast, I knew I wanted to take Rapamycin going back to 2011, 2012, again, based on just the data in the mice, the yeast, the flies, the worms, my biggest fear was immune suppression. Your paper comes along in 2014. Now, all of a sudden, I'm feeling much more emboldened. Still not sure how to dose it. But again, if your paper suggested anything, 5 milligrams once a week was a pretty good place to start. Then triangulating from some of the data in Matt Kaberlin's dogs and some other folks, I sort of arrived at, I think I arrived at 6 milligrams once a week was the right place to go. What wasn't clear to me, and still probably remains unclear to me, is how to cycle it. I mean, I have a protocol where I think sort of go on for 8 weeks and off for 6, or I think it's on for 8, off for 5. So it works out to be exactly a quarter. But truthfully, you know, without more advanced testing, I'm really making it up. And therefore I don't like talking about it. I just did, but you know, I don't want to suggest that I know anything more than I'm extrapolating. That said, I definitely do get side effects from it. I get aphthous ulcers, not as many as I used to. So there must be some acclimation I'm having, but I remember I used to get aphthous ulcers in residency all the time. I mean, I don't think I went more than 2 weeks without a horrible aphthous ulcer in my mouth during my residency. And I remember the day I walked out of the hospital for the last time, never getting one again until I started rapamycin, you know, 12, 14 years later. That's been the only thing I've noticed. One other little thing I've noticed, which is really odd, is when I'm on it, and it's not surprising, my fingernails grow slower. For example, I'm not taking it right now, and this is going to sound dumb. I feel like I have to cut my fingernails like every 4 or 5 days.
Do you feel any benefits from either of them when you are on them, or not really?
Nope, I don't feel anything that I can comment on.
Mm-hmm.
Joan, you didn't see him before, but he looks so much older these days.
I bet you he looks younger.
I looked like a spring chicken until I started taking it. Nir, talk to us a little bit about your book. I want to kind of go back and talk about a couple things. There was some funny stories in there that I was unaware of, and I want to at least have you tell one of them. I had no idea that you were one of the reviewers on the University of Wisconsin program. I'm writing about this experiment in great detail for my book that will hopefully be out in the next 10 years. And I talk about the NIH monkeys and the Wisconsin monkeys, et cetera. But talk to us about, I don't know if you know this story, Joan. Do you know the story about what Nir found when he was doing this?
No.
So set the stage, Nir. This is the single biggest experiment ever on caloric restriction.
Right. We couldn't do longevity in humans, so let's do it in primate and make sure that we're making progress. So Wisconsin set up their experiment. They go for, I think it's already 10 years, actually. I'm not sure it was 5 years or 10 years, but there's the renewal, okay? Mm-hmm. And they write the renewal, and the committee meets in Wisconsin the night before. And we go first over our comments. I'm reading their preliminary data, and I see something very interesting. The elderly animals are, before the body weight were separated and parallel. And all of a sudden, the monkeys are older, but they're starting to weigh the same. Although they're calorically restricted, supposedly, there's a disappearance of the delta weight. And I'm thinking, first, maybe it has to do with aging. It just doesn't work as well.
Metabolic rates are slowing.
Right, something is slowing, I don't know. But then I'm noticing that those cohorts were started at different times. They had like 3 cohorts, I don't remember exactly, but 3 cohorts that were started at different time. So they were at different ages. But all of them in the last year, their weight disappeared. And I'm sitting in the committee and I said, there's only one possibility that I can think of that all cohorts are doing that, and that somebody's feeding the monkeys, okay? And not noticing them. And indeed, they're coming, those guys in the morning, and they say, before we start, we want to tell you somebody was feeding the monkeys.
Extra food.
Out of compassion.
Oh my gosh.
And basically ruining the study. The Wisconsin monkeys took a year break and were ad libitum fed.
But nobody talks about this and the difference between the NIA and the Wisconsin.
I know, and maybe there's no difference. But I'm telling this story for another reason, because you realize I have all those rats that are caloric restriction, because that's my positive control, right? So I'm going to Einstein and I said, I want, you're meeting the animal caretaker. Are they meeting? He said, yeah. I said, I'd love to talk with them. And very simply, I'm telling you, we're looking at aging, caloric restriction extends lifespan, and we're doing it in animals. And I'm telling them the story of Wisconsin. And since then, nobody did anything wrong, but I knew that those guys are with me. And
Right.
I said, it's better for those who are caloric restricted. They're less sick. They live longer. Don't feed them.
Right.
I love that story, by the way, because it speaks to the human nature of science, right? And at the end of the day, science is still an operational discipline, and you can have the most perfect idea imaginable. You can have the most beautiful theory imaginable, but it is so difficult to do clinical trials. And even though that was a trial in primates and not in humans, it's as complicated as any human trial imaginable. And whether it's that study or any of these studies we're talking about, the decisions you make can come back to haunt you forever. If you pick the wrong patient in which to study this, if you pick the wrong indication. I mean, I'm constantly amazed at how often science actually works out when you consider all of the permutations in which it could go wrong.
Absolutely.
All the washout periods. Did you wash out long enough? Did you not wash out long enough? These things amaze me. Let's pivot a little bit to talk about epigenetic clocks. They're getting a lot of attention lately. There was a paper that came out probably 3 weeks ago looking at some changes in methylation. Do either of you want to just take a stab at sort of explaining to the listener what an epigenetic clock is, given that we're talking about aging, and then maybe we could talk a bit about them?
With aging, there are epigenetic changes, which mean it's not the sequence of the DNA, right? But on top of the DNA, there is a way to control whether gene is activated or not. And one of the ways to control that is methylation, which is a relatively simple reaction. And methylation is one way where the environment interacts with our genome. And the methylation with aging are either increasing or decreasing. Both of them happens. And they very often, the consequence is change in gene activity. David Sinclair, in his book, you can see that I'm seeing it as one of the hallmarks of aging. David Sinclair really thinks that that's not only the major cause of aging, but also the major way we change that. Anyhow, Horvath and Morgan Levine and some other people around the world have looked at methylation sites and tried to correlate them to chronological age. Okay? And it's a big process. It's also with artificial intelligence. You have to take lots of methylation sites. You have to do and see the chronological age, but more important, and the most important thing is to distinguish between biological age and chronological age. And there's a huge body of work that really showed that methylation clocks, and they're in development, there's newer and better, that methylation clocks are good. They're really good clocks of biological age, in particular when you see if they predict mortality, for example, but also predictions of a lot of diseases, not all of them. And so all of a sudden, this methylation became not only an important biology, a predictive biology, a biomarker, but also became a business. And this is kind of available out there.
I mean, I think what's interesting to me is, are these changes all pathologic, or are some of them compensatory and actually good? And so is reversing a biologic clock going to mean you're in a better state or not? So it's independent things.
And I would add to that, I think, Nir, you and I have maybe even talked about this, or I feel like I've talked about it with somebody, so I don't know if it was you, but we don't know if a person has let's just say person shows up at time T naught and they have methylation status M naught. You then apply an intervention that is beneficial. You give them rapamycin, you give them metformin. You go down to, another time point. even if you have not undone methylation, how do you know you haven't done good that is proactive as opposed to retroactive?
Exactly. So it's one thing to have a biomarker that predict biological age, but we want much more than that. We want biomarkers to predict if we're targeting aging, right? We don't want to do phase 3 studies for every drug that we have and spend billions of dollars over 5 years to find that it doesn't work. We need something that will show us in weeks or months that it's doing that.
My fear, though, I just want to insert my concern on this, is every time I've looked at one of these, I have found the data to be somewhat unhelpful because I don't know what to make of them. So I just had a patient use one of the very famous clocks. So he's a healthy guy, So his baseline test said he was 34. His biologic age was 34, which was younger than his chronologic age. So you are to the gate, you're thinking, well, that's already great news. So then we put him through a 5-day water-only fast. It's a pretty extreme measure. And then we checked a blood test immediately after, and sure enough, on the same biologic clock, his age went down to 27. So does that really mean that in 5 days of water-only fasting, he got 7 years younger? I mean, it's nonsensical to me, truthfully. And I find it a little bit annoying that people look to these clocks as though there's some, stone that comes from a deity that tells us something. Like, you can reverse engineer these things in any way you want, actually.
Right. And I think that's the problem. I think that methylations are kind of stable. So what we've been doing, we had a Nature Medicine paper at the end of last year with Tony Weiss. I don't know if you know Tony Weiss, Corey from Stanford, and we had a paper just accepted too, but we were looking for proteomic and doing a clock from proteomic. So I have a study where I took 1,000 patients between the age 65 and 95. And by aptamer technology, we looked at each one of the 1,000 patients on 5,000 proteins. And we asked, what does change between age 65 and 95? And we got hundreds of proteins. The most important thing about the proteins, they were a bunch of proteins that were breakdowns, okay? Breakdowns of collagen, of matrix, of granulocytes, of platelets. And initially I said, oh, give me a break. That's, what do I do with that? Coming to realize that that's possibly the best biomarker that we have, because no matter what we're going to do, whether it's with rapamycin or metformin or autophagy, what we're going to do is stop the breakdown that is typical to aging. And also proteomics are much more reactive than methylation, I think.
Although Peter just said in 5 days, the methylation responded.
Well, and in fairness, I don't know how much of that clock response was methylation versus the other biomarkers. So these commercial tests are using methylation is one thing, but they're using glucose level, insulin level. They're using a whole bunch of biomarkers. And again, I just know from having looked at the inputs, you never know what the algorithm is, but you know what some of the inputs are. Vitamin D level is one of them. Well, you take somebody whose vitamin D level is 20, which is low, you could give them 5,000 units a day and normalize it. And that change alone improves biologic age in a manner that's simply inconsistent with a single clinical trial that has ever suggested you can extend life with vitamin D. And so these are the problems I have with these things. But I agree, to me, the really interesting stuff is at the metabolomic, proteomic, transcriptomic level, of which maybe methylation becomes an additional thing that matters. But I think I just struggle with any one of these things being a magic bullet. But again, I might just be too jaded on this one.
Well, there is an aging cell paper where somebody tried to rejuvenate the thymus. And they took patients and gave them growth hormone, right?
Growth hormone, metformin, and DHEA.
Yeah, I was hiding that. I think it's a metformin effect, but they showed methylation reversal. So I don't want to say that methylation doesn't go back. I don't know this biochemistry to be like that. And I'm doing lots of methylation on my centenarians and their children. And so I'm like you, I'm excited of other omics and their potential as biomarkers that change with aging.
And I'll just say we've done some of this at Novartis with proteomics and aging. And the problem is some of the proteins that go up with age are actually, they've been shown in the Framingham Heart Study to be beneficial. Like it is a compensatory good thing. So saying, oh, I'm moving my proteome to a younger age can sometimes actually be bad clinically. So that is part of the mix.
Absolutely. When we get the proteome, that's why I looked at the breakdown. When you look at the proteome, you don't know in fact, a lot of them we know are compensatory, like GDF15, MIC, right? There's a lot that are obviously are beneficial, and we don't want to take them down, but we need to find the ones that are moving most. I want to say two more things about the proteomic data. Of those 1,000 people, 500 are children of centenarians that we know are slowing much, much later, and we published about them. They had about a third of the proteome of the 500 that are just usual people who are aging. So we have some relationship to longevity. Mm-hmm. Also, really interesting, and I think, Peter, this is worth a whole program. The gender effects of aging are so incredible, and we've missed them in every model, in mice, in rats, in humans. But while in men there are 700 proteins that are changing, actually 560 that are changing, in women there are only 200 that are changing. The proteome of women is much more stable. Okay, so we'll need to think of different biomarkers that are sex dependent, not only common to all aging.
Why do you think that is, Nir?
Well, we don't know. It's not as simple as saying sex chromosomes, okay? It's much more complicated, and I can get you to people who have NIH grant with lots of innovative ID to do that. You know from the ITP that it's all sex dependent. Thanks God that they did it. There was a discussion whether we should do it at all, but it's different.
Could it be possible, if it's not sex chromosomes, that it's endocrine related, and because women go through menopause, older women have a more homogeneous, because even with HRT, you'd think that would mess that up, huh? That's interesting. I wouldn't have guessed that, by the way. If you'd turned that into a multiple choice question, I would have got that one wrong.
Well, I foo-fooed the idea that women live 2.5 years long was like a fact that I didn't go on and thought that, even if we cure heart disease today, we're not going to get 2 years back, that this is huge. And we said, yeah, but they live longer and they are sick. And there's some truth to that. But I think there's the rate of aging itself is actually different. And a lot of the ITP, what they do in male, they get them to the lifespan of females, right, in the mice.
Going back to the idea of aging more broadly, bringing it back to your centenarians, I think there is, I think some people talk about centenarians as being escapers versus survivors, as you put them. I talk about this with my patients a lot. I talk about centenarians having a superpower, and our goal is to understand the superpower and try to emulate the superpower. And the way I describe it to patients, which is based very much on your work, Nir, is that their superpower is not that they survive better when they get diseases. It's just that they phase shift when those diseases hit them. They just, when they're 80, they're just acting like physiologically 60-year-olds. But, once they get cancer and once they get heart disease and once they get Alzheimer's disease, they're not bulletproof. They just happen to be able to dodge bullets better. So then I invoke images of, Neo in the Matrix and things like that. Do you think I'm interpreting your research correctly, or do you think that they are super survivors and who actually can take bullets on the chest and have them bounce off?
No, look, their aging is slowed. And when I'm saying they're aging from an age-related disease perspective, they live 30 years longer than a cohort that's 20 years younger than them. I mean, their friends died when they were between 40 and 60, so they already more than doubled life expectancy, right? Their aging has been delayed. What happens, though, their aging has been delayed enough to prevent major age-related diseases, but it's not obviously that they didn't age. So when they get to their end of life, they are just almost frail enough that whenever disease they get, it kills them. Okay? I don't know that I want it out that like that, okay? Because they still live longer, still live healthier, and still have a contraction of morbidity. But why does it happen? Because they're old. I have always this argument, like with Tom Pearls, who's doing centenarian study. I said, I don't care how they look when they're 100 years old, because now 30% of them will die next year. So no matter what I measure, it will either be the predictive of their death next year or the predictive of their longevity before.
Right. The better thing is, when they were 80, how do they look compared to their 80-year-old non-centenarian peers?
Right. And so we have their offspring who are now becoming 80. And it's really interesting because the offspring inherited only half of their genetic makeup, right?
Mm-hmm.
But they're so much healthier than control. I think our best paper was in American Journal of Cardiology when we showed their habits. Well, their BMI and their food intake and social economy and everything like that. But they had 40% of the heart disease of the control. Okay? So genetics plays a major role here, and it slower their age-related diseases.
Nir, you were quoted in an article, maybe it was taken out of context, but it was very recent, and the quote is something to the effect of rapamycin could reduce the morbidity of COVID-19 by 50%.
Maybe it's out of context. I'm referring to Joan's phase 2B study where severe disease was decreased by 52%. Am I right, Joan?
You are right.
With that, Joan, what is your dream experiment right now? If you could go right back to Restore Bio tomorrow and say, guys, we just got an unlimited amount of funding to do the definitive experiment, and the FDA came in and said, guys, the stakes are high enough. With the appropriate monitoring in place, we're going to let you go right to a phase 3 trial. What experiment do you want to do right now to test the hypothesis of this agent with respect to immune function?
Yeah, I would do the phase 2B as a phase 3. I would do lab confirmed respiratory tract infections, including COVID-19, and just show that elderly people who take RTB101 have decreased severity of illness.
You would not include RAD001. You would just do RTB101 versus placebo?
So in our phase 2A, we saw that the benefit for RTB was better than for everolimus, but why not?
It's a dream experiment. You can have 3 arms.
Add a rapalog too. Add everolimus, add RTB101. I wouldn't add the combo because that didn't work as well in our phase 2B. So I'd use those head to head and just show we could decrease the severity of illness.
And now to the point that says these are things that presumably have to be in the system before you encounter, these aren't drugs you start giving patients who show up sick. How would you then think about the on versus off cycle of the drug specifically? Would you dose it as 8 weeks on, 4 weeks off? I mean, what would these patients be enrolled to take?
So there's a peak of hospitalizations and deaths in people, particularly 70 and older, right during 4 months of winter cold and flu season. So that's when I would give it to them, where there's the peak incidence and peak healthcare resource utilization. Take it during that period and show that we have decreased hospitalization, decreased severe symptoms.
So your view is that the benefit is coming when they're on drug, not post-washout.
Exactly. There may be some benefit post-washout, but we saw that in the phase 2A. In the phase 2B, we didn't have enough events after they stopped taking drug because the season was over.
Mm-hmm.
So where I'm most confident is while they're on drug.
Okay, that's interesting. So that's a big deal.
I had a webinar that I called To Be or Not to Be, and the 2 was the number 2. And it's an ethical dilemma. We are at war. now, okay? This is not normal times. And we're at war, like when we went to Iraq, we chased Saddam Hussein, we chased the terrorists, but in the meantime, we had to also build better Humvees, right? To defend the soldiers, right? We have to attack the virus and we have to defend the host. And you have Joan who's telling you very convincingly of many studies that showed that immunity was improved, and the price from a matter of side effects, the safety was actually the safety profile were better because it was treating their aging too. And you have metformin that's been in so many years out there. We know that it's safe. So should we actually come and say, it's a war. You cannot stop the death of the elderly. Why don't we do those studies and monitor them? It's not going to be controlled. But is there something that we lose? Are we putting them in enough danger? Tell me. You're a clinician. You're such a thoughtful guy. What would you think we should do?
Well, first of all, Nir, you give me far too much credit, but I understand your question. And I think it's, a question of risk versus reward, and those are not static. And what you're basically saying is, when you ask this question in the summer of 2020, it's a very different question from what it was in the summer of 2018. And as such, our regulatory environment and our appetite for risk had better have changed in those 2 years, or else we live in a static risk environment and we're not adaptable, and therefore we're really ineffective. So in many ways, I struggle with this all the time, guys, because I don't prescribe rapamycin to my patients, though a number of them have asked. I prescribe metformin to my patients, some who need it for the standard indication of hyperglycemia, hyperinsulinemia, but a number who say, look, Peter, I've read enough of your stuff. I've listened to enough of your podcasts. I want to, I want to take metformin for these other benefits. And look, I think it's completely ethical to do so. They're paying for it out of their own pocket. It's not like we're asking an insurance company to buy it for them. So that's fine. I don't know what it is with rapamycin that has me hesitating a little bit more, though I would completely concur. It is probably as safe as any other. In fact, I feel less nervous taking rapamycin personally than an antibiotic. Every time, I had to take a cephalosporin a year ago. I was like, God, I just don't want to take this drug. So we know that these drugs are safe, but yet there is still some hesitation in me. And that waffling speaks to, I think, a broader issue. Now, of course, that's at the personal level as a clinician who has to make that decision with each and every patient. I do think that what we have talked about today, I think it needs to be on the radar of whatever entity is going to be self-appointed as the czar of getting us through this mess and all subsequent messes. I was on a podcast with Stanley Perlman recently, and we talked about how do you think about the no regret moves that need to always be in place for the subsequent pandemics. Like, there are just certain things that we should always have in place, right? We should always have a national stockpile of PPE. We should have a national stockpile of every reagent you would ever want to do PCR. We should have a national stockpile of any form of, antiviral therapy or immune modulating therapy that could be effective. And then, of course, the moment we find out about viruses and we sequence a new virus, we should have the infrastructure in place that we can rapidly test and have the electronic infrastructure to do the appropriate amount of contact tracing and surveillance. But somewhere along that way is, why wouldn't we also in parallel have an enormous path around doing rigorous research around immune enhancement? So I'll give you an example. Why hasn't someone done the definitive study to test the effect of sleep on immune function? Really, let's put this to rest and be done with it. Does it matter if you get 8 hours versus 6 hours of sleep? And if so, how much does it matter? Does vitamin D matter? Does it matter if you get it from the sun, or does it matter if you supplement it? Does vitamin C matter? You can say, oh, but Peter, each of those studies would cost tens of millions of dollars, to which I say, and shutting down the economy of this country cost how much?
It's such a good time. Yep.
Right? So I completely agree with you, and I would love to see a full out scientific assault on these questions. And obviously, my view is that there are agents like metformin and rapamycin that could play a significant role in preparedness. And basically what it really comes down to is resilience. I mean, that's really what you're talking about, is host resilience. These are not drugs, as you say, that you want people taking in the ER when they're already sick. These are drugs that you should have taken long before that so that A, you don't get sick, or if you do get sick, it's less severe, as the Chinese data that were published a week and a half ago suggest.
Or before you immunize, when you'll have the immunization.
That's right. I could keep talking about this stuff forever. Anything else that you guys want to talk about with respect to this particular subject matter? I want to be kind of mindful of our time. I know we've been chatting for quite a while here, and
I was thinking the dose response to you had asked me, would you use a rapalog early or late in the disease? Low doses you'd use to prevent. High doses, that immunosuppressive doses, actually might have benefit for that overreaction of the immune system.
That's really, really interesting. So has anybody talked about that, which is when you have that patient who is now in the second wave where the immune response is what's going to kill them, you hammer them with 20 milligrams of everolimus on 3 consecutive days or something. Anybody discussing that?
There was a small study showing, I think it was out of Hong Kong, showing there was a benefit in patients with severe influenza. And I think there's one trial looking at rapamycin in hospitalized patients with COVID. So I think the jury's out. People are thinking about it, but whether it's going to work or not, nobody knows. But the other thing I wanted to bring up to your point, Peter, is I do think these shouldn't be used until we prove that they have benefit. And I think Nir's going to get some really important data from metformin. Hopefully, RestorBio or someone will start getting placebo-controlled, really compelling data showing where there is and isn't benefit of these drugs.
Yeah, you don't personally take these agents yet, I'm guessing.
No.
And that says something, right? I mean, do you think of yourself as a particularly risk-averse individual, or is that just sort of the way you think about things and unintended consequences?
I like data. I want the data to decide what I'm going to do. So I want to generate the data. If I would want to be in a clinical trial where there's data generated to say, what is this doing, so that we learn?
Yeah.
I want to say 2 things. I think for metformin, what needs to be considered is that TAME will answer some of the questions. Let's say we decide we don't know what to do. We're going to give metformin now, okay? Because people are dying. The TAME study will provide, maybe later, but will provide some more evidence. It could be a little bit different, but I actually want to say something else. To the scientists, to Joan and the scientists, no matter how it's going to turn out, I believe that we won. Science won here. The scientists have been much more popular, right, than the president or other things. Science has won. You could see that the Pope is asking people not to go to church, right? And rabbis are asking people not to go to synagogues. And Ramadan was not in mosques. So there was an influence. And the influence was because they saw that we know and that we are responsible. And I certainly don't want to change that, okay? That's why what I'm saying is an ethical dilemma. But as a physician, I don't want to see studies that are not clinical studies, right? That's my whole shtick here. So I think we won, and we need to find how we do things effectively as fast as possible, and that it's still led by science.
The last point I'd add to that, Nir, is it has to do also with, I think, how you get to the stage 2B, right? Which is if you look at oncology, I mean, why does oncology have such an abysmal track record in clinical trials? Well, it might be that a lot of the preclinical work is subpar. It's being done in animal models that are not particularly representative. It's being done in cell lines that are not particularly helpful. And so it's really less about what are we doing in phase 3 versus how efficient is the pipeline to get an agent into phase 3. And so I guess to go back to your question of me a minute ago, I would say that the other thing to be thinking about is how much more efficiently can drugs be scrutinized in the pre-phase 2 so that you're taking better things into phase 3, because there everybody wins. The investor wins because you just have a much more efficient ROI. The patient wins because the probability of success to failure goes up, and then society wins because you're basically improving outcomes broadly, not just at the individual level. And again, I think it speaks to all these challenges we've talked about, which is what's the right question to ask? What is the right outcome? What is the right indication? And how, you alluded to something earlier, which is, look, the ITPs early enough figured out you better be really clear on which animals you're studying this in, or you will miss effects. And so I don't know. I just think, I don't know if enough time in science goes to this type of question, because it's not a very sexy question, right? Like if you're myopically focused as a scientist on your problem, well, then that's all you want to think about. You don't really want to think about these broad structural things of reproducibility and blind spots and things like that. But I think you have to start thinking about, when I say you, I don't mean you individually. I mean, we collectively have to be thinking about those things if we want to accelerate therapies to the clinic safely.
I think the other thing, Peter, that people don't oftentimes think about is there is the issue of regulatory authorities. You're absolutely right. You have to get the phase 2B right, but the FDA has never had a drug to give immunoresilience and decrease all sorts of infections. So they have to figure it out. And I think we also have to have a little bit of willingness to have a learning curve here to figure all this stuff out with the regulatory authorities. And we don't always have complete control over these designs. And we're going to have to they educate us, we educate them, and have an iterative process.
And I think your phase 3 demonstrated, I'm joking always that geriatricians are telling their patients, if you wake up in the morning and you have no pain, you're dead, right? So this idea that the FDA decided to take 75-year-old people and have a subjective assessment of how they are, it's crazy. It works if you're young and have arthritis, you will say if it's gone or not. But to elderly people about their health, they'll complain no matter what, or they'll shut up no matter what. You're not going to get a signal like that. So it's just crazy sometimes what the loops that you have to go through, and they lead you terribly.
And it's just life. I mean, the FDA admitted they're trying to learn too, but I think there's this perception that, oh my God, a phase 3 failed. That was because it's, people don't know what they're doing, or the mTOR doesn't work. It's so much more complicated than that. As Peter, you were referring to, there are so many ways for things to go wrong that sometimes you can control and sometimes you can't, but we have to have the perseverance to go, hey, let's look through this and see what's there and what isn't.
If there's a silver lining in the last 4 months, and I think there are a couple, right? If we're going to be brutally honest, I think, for example, many more people have figured out you don't have to get on airplanes nearly as much. I don't exactly have any love lost for the airlines, so that's certainly a win. But I think to your point, Nir, I think biomedical research has been elevated a notch. And look, if the right studies can be done, and that, by the way, goes back to something that we haven't discussed, or you discussed earlier, but I think we should bring back to your question, which is better biomarkers. Better biomarkers is going to allow for better studies, bottom line. And right now, our biomarkers are so crude as to border on unhelpful at times. So imagine you could, 3 months into a study, have a biomarker that tells you you're on the wrong direction, you're on the right direction, you need to pivot, you have a phase 3 design that is flexible enough to allow you to make the dose change or take a certain patient out of the study. And, these things matter because of the cost and the logistics of doing this study. So look, a lot of those things, again, they're not that interesting to people. Who wants to study biomarkers? It's not that fun. But I think we are in a new environment, and I think people are going to say, wow, we really need to invest in biomedical research, even for something that's not an immediate threat, like immune enhancement. Guys, thank you for tolerating me through a very awkward 3-person video interview.
Thank you so much.
Thank you.
Thank you for listening to this week's episode of The Drive. Head over to peterattiamd.com/show notes if you want to dive deeper into this episode. You can find me on Twitter, Instagram, and Facebook, all with the ID Peter Attia MD. You can also leave us a review on Apple Podcasts or whatever podcast player you listen on. This podcast is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. No doctor-patient relationship is formed. The use of this information and the materials linked to this podcast is at the user's own risk. The content on this podcast is not intended to be a substitute for professional medical advice, diagnosis, or treatment. Users should not disregard or delay in obtaining medical advice from any medical condition they have, and they should seek the assistance of their healthcare professionals for any such conditions. Finally, I take conflicts of interest very seriously. For all of my disclosures and the companies I invest in or advise, please visit peterattiamd.com/about, where I keep an up-to-date and active list of such companies.